Okay, so we've completed all the theorems that involve angles with circles. Now we're going to talk about segment lengths and some of their theorems. So our first theorem is if we have two chords that intersect in the interior of a circle, then the product of the lengths of the segments of one chord is equal to the product of the lengths of the segments of the other chord. So we're going to multiply the pieces together. So let me show you in the diagram to the right. So I have two chords that intersect at P. So let's start with chord AD. It's broken up into two pieces. There's AP and there's PD. Product means to multiply. We're going to multiply them together. So AP times PD, that's going to equal the pieces of the other chord, BP and PC. It's a nice easy theorem. Just multiply the pieces together. So now we'll do some with numbers in them. So my first chord, the pieces are 6 and X. So 6 times X equals the other guy, he is pieces 12 and 4. 6 times X is just 6X. 12 times 4 is 48. Divide both sides by 6. And we get that X is 8. All right, a little more complicated example here. So it looks like I have a diameter that's perpendicular to a chord. This was a very an old theorem. If that happens, these two pieces are equal. So if that's X, so is that. So we have to know our other theorem still. So for this chord, the two pieces are X times X. The other one, okay, so this piece is definitely 5, right? But I need to go all the way up to the intersection, okay? So let's think about this here. All right, actually, let's grab the other piece a while. The one piece is 2. Then I need to find this entire piece. Well, if that's a radius of 5, this is also a radius of 5. So if that piece is 2, then this little piece is 3, making from here to here 8. A little tricky knowing some other facts about circles. X times X is X squared. 2 times 8 is 16. Opposite of squaring something is our square root. And we get 4. All right, last example we'll do together. The two pieces here are 12 and 3x plus 1. If I'm going to multiply an entire binomial, I want to use parentheses. Equals, the two pieces for the next chord are 8 and 24. All right, let's distribute that 12 in. So 36x plus 12 equals 8 times 24 is 192. Subtract the 12. 36x equals 180. Divide both sides by 36. And we get 5. So the other way people like to remember the formula is just part times part equals part times part. All right, there's 3 of those for you to try on your own. You can pause here and work on those. I'm going to move on. Okay, our next theorem looks very wordy. It will be easier when we actually go to do one. All right, this time we have 2 secants. Remember, a secant goes past the circle and hits twice. So I have 2 of those. So if two secant segments share the same endpoint, that's M, they share M, outside a circle, then the product of the length of the secant segment and the length of its external segment equals the product of the length of the other secant segment and the length of its external segment. Okay, so some people like to think of this as, I'll simplify the formula, whole times the external piece equals whole times the external piece. Okay, I'll show you on the diagram. So this whole secant is from M to O. That gets multiplied with just the outside piece. So this is the interior piece, NO. The exterior piece is MN. I'll label this is the whole, and this is the external piece. That's going to be equal to, we're going to do the same thing for the other secant. The whole is from M to Q, and its external piece is from M to P. We don't need the internal piece, okay? Unless it's helping us calculate the external piece or the whole. So the whole times the external. All right, let's try a couple of these. All right, so let's start with the top one. I need the whole thing. Biggest mistake I see, because we know we need these two pieces together, is people write 8x. That means multiplying. I don't multiply this piece times this piece to make a whole, I add them. So it's 8 plus x, okay? Or x plus 8 if you like the variable first. So I'm going to be using the whole and the external piece, multiplying them together. I have a binomial, so I know he's going to go in parentheses. So 8 times 8 plus x equals, all right, my whole here, right, just like you wouldn't multiply these to find the whole, you would add them. 12 and 20 make 32. Times the external piece is 12. And now we solve. Distribute. So 64 plus 8x equals 32 times 12 is 384. Subtract the 64 over. So we get 320. Divide by 8, and x is 40. All right, let's take a look at the next one. I need the whole. So this whole thing, 5 plus 7 is 12. Its external piece is 5, so this part will be 12 times 5. All right, the next one. Notice the whole is already given to us. I don't need to add the two things together. The whole is x times, and the external piece right there is 4. 12 times 5 is 60. X times 4 is 4x. Divide by 4, divide by 4. And we get that x is 15. All right. Next one, a little more complicated. All right, looking at AC first, my whole's given to me. There it is, it's 12. Now, the external piece is right here. It's not given to me, but if the internal piece is 6 and the whole is 12, then this piece must be whatever 12 minus 6 is, which is another 6. Right? So you may have to find the external piece. All right. This next part, the whole. Okay. Now be careful, it's not just 4 plus x. X is just referring to this little radius. We're missing this piece, but if you notice, that's just another radius. All radii are equal in a circle, so if that's x, so is that. So if I add 4 plus x together, we get 4 plus 2x, right? We gotta combine like terms. So there's the whole. And then the external piece is the piece out here, the 4. I'll put the 4 first, just because I know I'm gonna use parentheses on the 4 plus 2x. All right, let's solve. 12 times 6 is 72. Distribute. 16 plus 8x. Subtract 16. We get 56. Divide by 8. And we get 7. All right, there are 3 of those for you to try. You can pause now or wait till the end to do them all. I'm going to move on to our last theorem. All right, our last theorem is for having a secant, but instead of having another secant like we just did, we have a tangent, okay? If a secant segment and a tangent segment share an endpoint outside the circle, they share u in this case, then the product of the length of the secant and its external segment, so just like what we did last time, will be whole times external for the secant. So I'll show that. We'll be doing the whole and the external. We'll even do that right away here. So the whole is uy times the external piece is ux. Now, we don't have a secant here. This is a tangent, so this is going to have a different rule. So we'll keep going here. It will equal the square of the length of the tangent secant. So this is my tangent from u to v. It's going to get squared like that. So if you want to like memorize something simpler, you can memorize whole times external, just like the other secant, equals tangent squared. Okay, let's practice some of those. We'll start with my secant. The whole thing is 9. Its external piece is 4. So 9 times 4 equals, here's my tangent, that's going to get squared. 9 times 4 is 36. Opposite of squaring is square root. And we get that x is 6. Okay, let's try another one. Finding my secant, we're going to do the whole. Remember, we're not multiplying those, we're adding them to find the whole. So it'll be 3x plus 5. That's the whole. There's the external piece. So 5 parentheses, 3x plus 5 equals my tangent over here, 10, it gets squared. Distribute, 15x plus 25 equals 100. Subtract 25. Get 75. Divide by 15. And we get that x is 5. All right, this last one is the hardest one. And we're going to have to remember how to factor from Algebra 1. I'll walk you through that. All right, so let's find our secant. Let's do our whole. The whole thing would be y plus 15. Its external piece is y. So I'm going to be doing y times y plus 15. equals, here's my tangent. My tangent happens to be 10 again. That will get squared. All right, let's distribute. Y times y is y squared. 15y equals 100. All right, so I have a y squared term, and it's not that simple like this one where I just have an x squared and it's over, because I have another y. So when I have a quadratic like this, I'm going to need to get it equal to 0 before I factor. So I need to subtract the 100 from both sides. Notice none of these three things are like terms. So it's going to be y squared plus 15y minus 100 equals 0. Now that it's like that, I have a trinomial to factor. First spots are y's. So as a reminder, to factor this, we need to find two numbers that when I add them, I get 15, but when I multiply them, I get negative 100. Let's start with the fact that I need to multiply to make negative 100. If I need to multiply to make a negative, the only way to do that is to have a positive and a negative. So those must be my signs. All right, so if I think of the factors of 100, I have things like 1 in 100, 2 in 50, 4 in 25, 5 and 20, 10 and 10, right? All right, so those are all positives though. So you want to imagine that one of them would be negative and they're going to need to add to 15. Well, that's looking like this guy if I were to make the 5 negative, because negative 5 plus 20 is positive 15. So the plus sign gets the 20, the minus sign gets the 5. That's how we factor trinomials. Then we had split to solve them, setting them each equal to 0. Subtract 20 from both sides. And one of our solutions is 20. Negative 20, I mean. And then over here, we're going to add 5 to both sides. And our other solution is 5. So then the question is, can there be two solutions? Well, maybe. I mean, things can have more than one solution. But let's think about that if this would make sense in terms of our picture. Look at where y is. Y is this segment length. Can a length of a line be negative? No. So that gets rejected. So we only have one answer of y equals 5. Okay, you have 3 of those to practice on your own. And then the last sheet mixes all 3 theorems together to practice it again and make sure you know the difference between all 3. And that's it.